All right, let's continue our work here on neuroscience of motor control. All right, cerebellum. Ooh, 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 ooh. Y'all, cards on the table. The cerebellum is probably my favorite part of the brain. Seriously, it's the weirdest, it's powerful, it's not fully understood, its impairments are really challenging to treat. It's such a mess, and I love it. Okay, cerebellum, who is she? The seat of coordination. Processes sensory info so that you can actually stand up straight and walk in a coordinated fashion. Huge part of motor planning, which we'll get into later. It doesn't talk to the lower motor neurons directly, more like it talks to M1 and everybody else, and fine tunes things because one of its big jobs is a comparator, which we'll talk about here in a second. So it's way back at the back of the skull, still not fully understood. Part of the way we understand it, actually, in terms of like these odd tone and language functions, as well as the acquisition of gait, are actually in some very, very unusual cases in which people were born without a cerebellum. There's some case studies on that. Let me know if you want to know more about that. They're fascinating. But in these cases, there's one woman in particular that I recall the case study, and she did not acquire walking until I want to say age 7 and full production of language and speech until like age 5, I want to say. At any rate, so clearly it plays a role, but it's just one of those strange things. Okay, so the cerebellum, one of its main functions is to produce glorious, beautiful, smooth, coordinated movement. Yeah? It's a good one. It really is. This super weird looking image right here is actually the back of the brainstem. So if you were like looking at the back of someone's head and you cut away the cerebellum, this is what you would see. So all of these structures just the cerebellum talks to. I mean, talk about influencing motor control on a high level. It's talking to pretty much everything. Okay, brainstem. It's in front of or anterior to the cerebellum. So here it is. Right around here, you become spinal cord. So it's critical to life. I mean, it's got all your centers for your heart rate and your breathing and vomiting, actually, vestibular nuclei, all kinds of cool stuff. All of your tracks go through here. Cranial nerves, quite a few of them live in there. Yeah, all major sensory and motor goes through the brainstem, so don't hurt it. Okay, there's 3 main parts. Look, team, you've already had neuroscience, so the truth is this is a purple hexagon slide. It's just nice to know. You really don't need to know the function of each part of these for me. This is just kind of here in case you like. So one thing I would always note is that the midbrain has some really interesting structures in it, but it's not really anything that you need heavily for motor control. The pons is where the vestibular nuclei live, as well as the VOR, and it's kind of like it controls a lot actually. The pons, medulla, critical to life. Oh my God, respiration, heart rate, blood pressure, your guts doing their thing, vomiting. Oh my goodness, a ton of cranial nerves. Medulla's got a lot. It's got a lot, but you don't really need to know that slide. Okay, now for my absolute most favorite science thing, the vestibular system. Vestibular is notorious because it's detail oriented and highly specific, so it can be really confusing when you first learn it. Don't feel bad if you're like, what is this? Totally normal. Because it's not specifically one structure, it's a bunch of things in combination because that's just vestibular. So it's stability of the head and the body in space. It's different things activating so that you're not, falling over. It's your ability to focus your eyes on targets, particularly when they're in motion, you're in motion. It's got a lot going on. Its job is specific and powerful. So, what does it actually perceive? Well, it detects linear acceleration and angular movement, the relationship of structures to each other, particularly us versus the world, as well as speed of changes in position. So, if you've done some sort of sport with a very, very high balance component, such as cheer, gymnastics, some sort of skiing, or diving, anything like that. Oh, ice! If I didn't say ice, like figure skating. Oh my gosh, speed of changes in position. This is powerful. As well as like skateboarding and biking and things like that. So if you're basically taking your head very, very far away from upright while not falling over, vestibular works really well in you. So what does it do with this information? Well, it provides gaze stability, your ability to keep your eyes on a target. Postural stability, your ability to not fall over. Orientation in space, knowing up from down. And postural riding responses. So you step on that icy ground, you slip, and your leg moves. The other leg and your trunk and your head and your arms are ready to help you out. Yeah? So subtle, yet very important. Okay, I do want you to know the structures that are considered central versus peripheral. Okay, you need to know their names. I do want you to know about these reflexes, like what their jobs are. Okay, so we're talking cranial nerve 8. You've already had neuroscience, so you know cranial nerve 8. It has two pieces. One is for hearing, one is for vestib. So this is the one we're talking about here. And of course, this is a peripheral structure. And once we get really deep into that cool looking structure there, this is the function of these two bad boys right here. See these jelly bean looking things here? Utricle and saccule. So without getting too deep into the anatomy here, because I can get into the weeds so very quickly, but we'll save that mostly for your second year. These guys have some very specific jobs, okay? And part of that has to do with the tilt of the head, which is detected through the coolest way ever. So here, look at this. Okay, so when you tilt your head forward, there are little structures that sit in a jelly. So these little structures are here, and they're made of calcium carbonate, which is basically like chalk. And when you lean forward, they sit on this jelly. So this image has got it better. So here's your calcium carbonate crystal, and it's attached to these little dudes. And these are actually like mechanically gated channels. So when they get pulled over, they open, and you get this flow of positive ions going in, and that's what actually causes your action potential to let your body know, hey, you've tilted your head. So there's two different parts that do this. So they're at different angles. Here's the utricle, here's the saccule. Same thing, different angles, yeah? So utricle is for horizontal, saccule is for vertical. So horizontal is like tilting your head left, right, and vertical is like tilting your head forward, backwards, okay? So they also have to do with acceleration components, which we'll talk about here in just a second. So the otolith structures, which are the utricle and saccule, they're for linear acceleration. So linear acceleration is tilting to look up or down, tilting to look like if you're like making one of those little like doggy that doesn't understand, like ooh, kind of looks, tilting your left ear to your left shoulder, as well as acceleration forwards or backwards. So if you hit the gas, that's linear acceleration, okay? Which is different from, and vertical linear acceleration is hard to create. It'd have to be you're falling straight down. So if you ride one of those things at like Six Flags or whatever that like takes you straight up, straight down, that sort of thing, that achieves it. That would do it. But it has to be straight up, straight down for pure linear acceleration that's in the vertical plane. Otherwise, yeah, these are interesting. So they, just a small note here. So the otoliths respond to linear motion instead of angular motion, and they respond to acceleration rather than gravity. So they would perceive that the car is revving, but not that it's going 30 miles an hour. So you can be on the highway, and if you're traveling like 100 miles an hour and it doesn't change, you can't really feel it. You know, you can see it, but you can't feel it, okay? So just a heads up on that. Okay, so again, I'm hitting it again. Linear acceleration and the position of the head in space. Yes, we love it. Why? Because there's these little chunks of chalk sitting in this cool jelly that trigger this little guy here, this hair cell, and basically allow the brain to know that your head is tilted down, okay? So the weight of these little guys drags the hair cells down to open the channels and activate them, okay? So you get the ions, positive ions flowing in, and then that's how you get the action potential. And that action potential is basically carrying sensory information regarding the position of the head, okay? So utricle and saccule, linear acceleration, position of head in space. Yeah, so basically neck flexes or extends, gravity pulls on those otoliths in the utricle and the saccule. Semicircular canals, so these are these guys, these big pretty arcs, okay? You've got 3 of them on each side, total of 6. They contain a fluid called endolymph. And when that gets shoved around, it's got a really thick consistently. I've heard it described as like almost the consistency of honey. Endolymph is really thick. It moves slowly. So to displace it, you have to get like a lot of force on it, and that's going to be angular velocity. Okay, so these are angular velocity. And that allows the brain to know a different form of information. So this one is detecting angular acceleration of the head through displacement of something called the cupula. And the semicircular canals operate through a push-pull pairing, which I'm going to show you here in just a second. Okay, so here's the cupula here. So that little dude is here. Okay, so this is easier to see. Okay, so we're in the semicircular canal here. Okay, so we're in these big, pretty arcs. We're in one of these. There's 3 of them. There's the other one. There we go. So there's 3 of them. And inside, they've got this little thing. Think of this as almost like a little flapper. It gets shoved if fluid smacks into it, okay? So if you turn your head cleanly to the left, like let's say your friend is like, hey, and they say your name, and you're like, what? And you turn your head real quick to the left to hear your friend, your endolymph is slamming into the cupula, okay? And when it does that, it triggers mechanically gated channels here that basically let you know that you have turned your head in an arc. That's angular acceleration, okay? Now, what's extra cool is, because you've got a pairing of these, you've got, a left ear and a right ear. So you've got semicircular canals on the left, you've got them on the right. And one of them basically turns on, the other one basically turns off. So one hyperpolarizes, one hypopolarizes. And when that happens, the one that's air quotes on, hyperpolarizing, that's getting the signal. So that's how you know which way your head is turned. So it's on off, or push pull. That's kind of how we create that idea. So if you're turning to the left, this left one is turned on, the right one is turned off. Yeah? And so that's how you know you're looking to the left. Okay, so again, different types of sensing. Angular acceleration, this is your semicircular canals. Linear acceleration, this is your otolith organs, okay? Yeah. So once again, so if you're spinning in circles, angular. If you're leaning over, linear. Cool. Okay, so like I said, these things are yoked. So what's really cool is, observe here. So this is the anterior canal. It is yoked to the posterior canal, and this occurs through nerves. So that way you kind of know your position in space, because remember, this endolymph is sliding forward when you tilt your head down to look at your toes. And that's also happening over here on the opposite side. So basically this one turns on, this one turns off, okay? So anterior talks to posterior. This one here in this context is anterior, this is posterior, and vice versa. So this one's anterior talks to this one's posterior. And then the 2 horizontals talk to each other. They're parallel to the ground, okay? But yeah, they basically work in like the most obnoxiously complicated way to let you perceive angular acceleration so that you know where you are when you're turning your head. Okay, so the reason this matters is for a reflex called VOR, the vestibulo-ocular reflex. So the eyes have to do the immensely challenging motor control job of staying on a target, and they have to do the same thing. They each have to do the same thing. If one of them is off, you're gonna have such a headache, you might even throw up. It's a lot of coordination. So your left eye and your right eye have to look at something at the same time. In addition, you might be turning your head. So in this context, this person is turning to look to the left while their target is going to the right. We do this all the time when we're driving, playing a sport, whatever really, but it has to happen in a coordinated fashion. In order to do that, the amount of movement that the head is performing has to be matched to the amount of motion that the extraocular muscles of the eyes are performing to turn the eyes to the right. So your neck is moving your head to the left, but your eyes are moving to the right. Yeah? We're going to do this during class so you can see it a little better. But it keeps your eyes on target. So if you're walking while looking at something and walking away from it, that's kind of when this kicks in. And so this push-pull system is really important back here. Remember those head turns? That's semicircular canals. So one of them turns on, one of them turns off. And this information coordinates back and forth with the muscles of the eye so that you're matched up. That match is called gain, G-A-I-N. And we really need it to be 1-to-1. If it's not, then one of these is going to move too much or too little, and you're going to be off, and you're going to know real quick. You're going to have vertigo very quickly. So, okay, so all of that is to give you a sense of the motor control of the eyes in relation to the head moving, okay? And a lot of central structures can contribute to these things. This image, you don't have to take anything from this image other than it's stupid complicated. Look at all of these structures that have to talk to each other, and this is all structures of the brainstem here, with the body, the semicircular canals, the eyes, everything in order to keep you upright in space. Vestibular gets complicated very quickly. You need to have a handle on all of your neuro, or it's really kind of challenging to understand. So just a gentle heads up on that if you're thinking of going vestibular. It's a passion area for me. I built a love of things that are dizzy when I was in PT school, and I kind of just kept steering my career in that way and never looked back. So if I were to not be, in academia, I would just treat dizziness all day, truly. Okay, so let's look at these things here, these reflexes. So putting all of these things together is crazy important because we're going to come back to postural control, and you need to know what's going on the inside. Postural control is a big topic. So here we are at VSR and VCR. VSR is one of my favorite things to test you on. You've been warned. Okay, VSR is the vertical alignment of the trunk. So if you are tandem walking, one foot in front of the other, that vertical alignment of the trunk is maintained by your vestibulospinal reflex. So if your head tips in one direction, the body elongates on that side and shortens on the other, but then it also might have to like snap back up. So that's all that sensory information, right? So that sensory information is coming in, and your head and your trunk are actually talking to each other, and that's how they know that those things are happening, and they snap the muscles to activate so that way you don't fall over. VSR is super, super important in the treatment and assessment of folks with a balance impairment. VCR is the exact same thing, but it is specific to the head. So it's your head positioned in space on your trunk, and it often gets injured very subtly in the setting of concussion and head injury. This one is the whole trunk, but it's really more just like T-spine and L-spine. This is more C-spine. C-spine, this is more thoracic and lumbar. Yeah. Okay, roll the cerebellum. Ooh, this is a guarantee because I just think the cerebellum is super important. Okay, so the cerebellum's role in all of this is error correction. It is a comparator. It compares the movement you actually did with the movement you meant to do. So the cerebellum basically yells at the cortex, hey, you did not extend that elbow enough, and that's why your throw had bad aim. That sort of thing. So it is so important for error correction, okay? It's also very good at timing, and timing and sequencing is how it does that. Yeah, it adjusts things. So to contrast this with the basal ganglia, BG, basal ganglia is rate and force. Cerebellum is adjustments, timing and sequencing. They are different. God, they're different. They seem similar, but actually they're very different. So in this context, this allows the cerebellum to help you with what's considered a skilled movement. So classic examples that you learn that are like kind of repetitive skilled movements: typing, playing a musical instrument like a piano or something like that, flossing, and discrete sports motion. So something that's very specific, like throwing a ball or dribbling, pitching. That's big. So that's the cerebellum. Okay, cerebellum is all get out. Those automatic things, you don't have to think about it anymore. When you don't have to think about something that's a skilled movement, it lives in the cerebellum. When you are thinking about it, it's over in the cortex. And it's important that things go over into the cerebellum because that's like your subconscious. It's very energy intensive to do something like think about walking. That shouldn't live there. That should live in more of your automatic parts of your brain, not your conscious parts of your brain. That's for doing stuff like talking and hanging out with your friends and thinking about, I don't know, philosophy, whatever. It's not for things like pick up your knee, bend your ankle, or whatever. That's the cerebellum's job. It does those skilled movements. It's also incredibly powerful in the learning of motor tasks. So new things. Okay, so what I want you to know here is that the vermis of the cerebellum is immensely important for trunk stability, and it's implicated in the VSR. So if you don't have it, you end up with what's called ataxia, which is where you have this really, really uncoordinated motion of the trunk relative to everything else. So we'll talk about this more in class, but it's the drunken stagger, okay? So when you don't have the vermis in good health, you end up with that drunken stagger in which the trunk looks like it's a top bopping around. That is truncal ataxia. It also has to do with gait ataxia, with the coordination of the feet, and basically sensory info from your legs is not getting used to stabilize posture, and that's how you end up with a gait ataxia and truncal instability. VOR, that gain we talked about, is controlled by the flocculus of the cerebellum. The nodulus allows you to process VOR responses and otolith inputs. So it's implicated in motion sickness, and some things here that we'll talk about later. So also gait ataxia. There's more than one form of ataxia of the legs, okay? Well, that's for your second year. But it also has to do with nystagmus, which is involuntary uncoordinated motions of the eyes. So these are the three structures of the cerebellum that you want to know: vermis, flocculus, and nodulus. What is their job and what does it look like if something is wrong? Okay. Ew, vestibular nuclei. So what you really want to know about this is that it's a relay for the VOR, and that it's actually here. This is what I want you to know. They're heavily involved in VSR. So if you're doing Romberg or tandem gait, we are perceiving VSR as a function of the vestibular nuclei, okay? They also play a role with eye and head movements, but don't worry about that. Okay, so here we are. So things to think about. You really want to pay attention to who is responsible for what across this whole lecture sequence. You want to know, if I've given you this information, what does it look like when something is doing its job or is not doing its job? And then, for sure, green and gold star material. All right, team, see you in class.